Okay, so where are we in lecture? Have you guys finished acids and bases? Okay. All right. So a lot of material to cover. This recitation is probably going to be the most important one this semester. I'm going to be covering the the most involved topics. Yeah, sorry about my voice. I've been down all week with laryngitis and all sorts, garden variety of things, but I think I'm well enough to teach today. Okay, so last time, so remember our mantra. This chapter is all about calculating the pH in different contexts, right? In some cases, you calculate pOH and then make the jump 14 minus to pH. We covered the easiest of these contexts last time, which is strong stuff, strong acids and strong bases. And today let's start with some of the weaker stuff. So weak acid or base pH. pH of a weak acid or weak base. And the topic that comes after this is mixtures of the weak stuff with its broken piece, conjugate. But we're going to focus starting with only pure weak stuff. So for example, vinegar. Vinegar is acetic acid. It's a weak acid. And so we're interested in figuring out what the pH of vinegar is. So here's an example. Another thing, calculating the pH means somehow, in whatever context you're given, you want to calculate the concentration of H plus or OH minus, right? So that's all we're doing. In the case of the strong stuff, we know all of the acid or the base dissociates into H plus and OH minus respectively. In the case of the weak stuff, we need to use ice tables to figure out of the total that we began with, of the initial amount, how much actually dissociates and how much remains undissociated. And to help us in this endeavor is our friend, the equilibrium constant. Because that has in it all the information you need. Equilibrium constant tells you how much of your acid dissociates in a given setting. Okay, so for example, calculate. Such a bad chalk. Calculate the pH of 0.5 molar acetic acid. So CH3 COOH, given that its Ka value is, let's say 10 to the negative 7. Okay, so what does CH3COOH break up into? It's an acid, right? So what do we expect on the other side?
CH3CO minus.
Yeah, so this is the broken piece. It's often easier to first start with what we know for sure needs to pop up on the right-hand side. Do a subtractive process, sort of. We know an H plus needs to pop up because this is an acid. And then now we can figure out what remains. That, with the minus. Right? So that's the broken piece. Yeah. Okay, let's draw an ice table. This is 0.5 originally. This is before any dissociation happened. Before any dissociation happened, did we have any pre-existing H plus or this? No, right? So these are zeros. In the next topic, this will be non-zero. Because we will start with some amount of broken piece, some amount of conjugates. That's the follow-up to this topic. Giving you a preview. Okay, so 0, 0 in this case. All right, tell me, what goes here? Change. Negative x, good. plus X and plus X, right? Reactants get negatives, products get positives. And so at equilibrium, we have the sum, 0.5 minus X, X, and X. Great. If we are able to figure out this X, X corresponds to the molarity of H plus, right? Take negative log, boom, we have pH. So that's what we're trying to do here. Okay, let's set up the equilibrium expression. What goes on top? Say that again?
X squared.
X squared, right? Products. Concentration of this times concentration of this, which is X times X. X squared. And on the bottom goes the reactant, 0.5 minus X. No coefficients here for any of the species, so no extra powers. This is not a power that came from coefficients, this is just X times X. Okay, so this is, now you have to be careful. Sometimes they trick you by giving you Ka when you need Kb and Kb when you need Ka. In this context, this is correct. I've given you the correct value. Because look at what pops up on the right. It's an H plus, so this is an acid equation. With acid equations, you have Ka. Ka goes with acids. Kb is for bases. And if you're ever in doubt whether you're dealing with an acid equation or a base equation, look what pops up on the right, whether it's an H plus or an OH minus. Okay. So this is 10 to the negative 7. Can I use small x approximation here? The Ka is pretty small, 10 to the negative 7. Sounds like it's a safe bet. So what gets dropped in this expression?
Minus X.
Minus x. The only term that's added or subtracted from a number. Yes, great. And so x squared over 0.5 is 10 to the negative 7. Solve for x. .5 times 10 to the negative 7. Which comes out to some number. How do I calculate pH? Negative log of that number. Great. Great. Any questions? Let's work with a base now, a weak base. Same question. I'm just going to make this a weak base. What's a weak base? Yeah, good. Thank you. NH3. Now you see NH3 doesn't have an OH in it to give off. Remember we have two kinds of acids, two kinds of bases, right? Depending on whether you give H plus or absorb H plus, give OH minus or absorb OH minus, and so on. So because this doesn't have an OH that you can see that can be given off, this must be the other kind of base that accepts an H plus. Does that make sense to everybody? Acids give off H plus, bases receive H plus, some bases. So you can write that like this to NH4 plus, but you shouldn't do that. Let me very quickly talk to you about alternatives to writing down the acid and base dissociation reactions. Usually what we do is this, right? We have an acid, we break it down into H plus and Cl minus. Yeah? This is a regular acid. What you can do also is react your acid or base with water and have the H plus that comes off from the acid, tack it onto the water. So now you get, instead of H plus, you get H plus attached to H2O, that's H3O plus, and the broken piece here minus. This is another way of writing acid dissociation reaction. H3O plus here plays the part of H plus. This is called the hydronium ion. If you do it like this, pH is going to be the negative log of, usually it's H plus. You can also write it as the negative log of H3O plus. Same thing. Okay. Why am I doing this? Because it helps to write down the base reactions for things like these. So for example, for that, NH3 reacts with water. This is the H plus absorbing kind of acid, right? It will steal that H plus from H2O. Okay, so it becomes NH4 plus, just like here. It's getting that H plus from water. If I remove an H plus from water, what remains? OH minus. Water is HOH. So if you take out an OH plus, you're left with OH minus. So now you can see that NH3 is indeed explicitly a base because you have an OH minus that's popping up on the other side. Make sense? So you do this kind of dance with acids. You can do it with bases that absorb H plus, but careful, you can't do this game with bases that release OH. So for example, NaOH breaks up into Na plus and OH minus. That's good enough. If you try reacting NaOH with water, nothing really changes. This dissociates to Na plus, OH minus, and the water just remains as is. Water appears on both sides, so you don't need it. Okay. So there is no use of reacting it with water. Because the reason is, water can accept an H plus. Okay? In the case of acids, the H plus that's removed gets tacked onto the water. That's okay. Water can handle that. Water can also lose an H plus, as in this case. What water can't tack on is an OH minus. Okay, you get it? So it can gain or lose H plus, but it can't do OH minus. That's too much. Okay, so in the case of bases that have an OH in them, just dissociate them normally. Don't react them with water. You don't need to. Okay. So let's do NH3. React it with water. This is the H plus absorbing kind of base. And so this accepts an H plus to become NH4 plus, and what's left of the water is OH minus. Great. Just like before, this is 0.5. Water is a liquid. Don't care. This is always true in these tables. Never care about water. Pure liquids, pure solids. You don't care. Undissociated as of yet, so 0 and 0. Minus x plus x, the usual. 0.5 minus x, x and x. The same thing holds this time, right? This is the correct equilibrium expression. I haven't done much changes, so this is it. And you use the small x approximation and so on and so forth. But here is 10 to the negative 7. So I've given you for this question Ka, which is 10 to the negative 7. Can I use that in my equilibrium expression? No, right? What do I need here? Kb. So if Ka is 10 to the negative 7, what's Kb? It's 10 to the negative 14 divided by 10 to the negative 7, which in this case happens to be 10 to the negative 7 again. Which is okay. But that's just, it's a special value. It's the square root of 10 to the negative 14. But okay, so in this case, when I do all of this and I solve for my x, I get a number. If I take the negative log of that, what do I get? pH or something else? Say that again?
POH.
pOH, right? Because x here now stands for the concentration of OH minus. So pOH would be the negative log of that number. And to get pH, you do 14 minus that number. All right. Any questions? Okay, let's move on. Yes.
For the problem for this one, we're going to subtract 14 minus the,
Mm-hmm.
why didn't we subtract it?
Oh, because the question's asking you for the pH, and what you can directly calculate by taking the negative log is pOH, because OH is what you know. Yeah, always true in base questions. Okay.
Alex is a little bit different. They don't do 14 minus, they do like 1 times 10 to the negative 14 divided by the x value. And that gives you your H plus concentration, I think. I'm not sure. But they do-
Yeah, you can do that. Yeah, it's remember there's two things you can do, right? There's two kinds of parallel relations always. You have the Ka times Kb. Oh, no. You have the H plus concentration times the OH minus concentration equals 10 to the negative 14. Or you have pH plus pOH equals 14. What you're doing is you solve for x, which in this case stands for OH minus, and so you do 10 to the negative 14 divided by x, that gives you the h, and then you take the negative log. It's like we're doing the same thing but switching the order in which we do it. I like to just do that. Up to you, totally up to you. Yeah.
Also, sometimes they also give like a pKa value.
Yeah. So for example, here we could have said that pKa is 7. Okay, if pKa is 7, what I need here is Kb. So first of all, I would calculate pKb by doing 14 minus, also 7, and then do 10 to the minus of that thing to get 10 to the negative 7. What?
How do you convert to pKa and pKb?
Oh, pH and pOH add up to 14.
Oh,
pK also add up to 14. The relationship between H and OH and Ka and Kb are complete mirrors of each other. Let me let me go over some examples. I promise you next time I will buy some high quality chalk and have a duster of my own because this is ridiculous. There was a duster last time, you guys remember, right? Now there's none. And all I have are these two little pieces of chalk. Hopefully that's it. I rode my bike yesterday at like 9 p.m. or 9:30 to a Staples to buy chalk. They had some very cheap chalk. I got it for like under $2, and then I forgot it at home. And so, oh, it's rough. Okay, so suppose you want KB, and what you start with is you have pKa. Oh, this one's nice. pKa to be 2. How do you get pKb? Just KB. pKb is 12. Good. So pKb is 14 minus 2, which is 12. I need KB into the negative 12.
Why did Alex make it so much more complicated?
Yeah, they like make us do all this other stuff.
Was there a question? Oh. Okay. Great. Moving along. Before we do weak and broken piece combination, weak conjugate combination, let's do. So So this is the logic that we're following. Pure strong species, so pure strong acids, pure strong bases. Pure weak species, pure weak acids, and pure weak bases. And now I'm going to do pure broken pieces. That's all. Okay, so this topic is pH of salts. That's what it's called. A salt is made of two conjugates. Salt is made of two conjugates. That's what a salt is. It's two broken pieces attached together. The two broken pieces, one comes from an acid, one comes from a base. You guys remember from maybe Chem 1 what an acid-base reaction looks like? Acid plus base gives you a salt and possibly a water. Okay? The water comes because you have an H plus and an OH minus reacting with each other. That gives you H2O. What's salt? Salt is what's left over of the acid and what's left over of the base. So a salt is two broken pieces attached together. It's two conjugates. Now, if you remember from last class, not all conjugates are pH active, right? Some of them are acidic, some of them are basic, and some of them are neutral, remember? Depends on where the broken piece came from. So just as a refresher, if you have a strong species, a strong acid or a strong base, it leads to neutral conjugates. If you have a weak acid or a weak base, then you get the opposite. So you get either a base or an acid conjugate out of it. So far, so good? This is from last time. So when we have a salt given to us, what we do is we take our salt, we break it into its constituents, its conjugates, the two conjugates that it's made of, and then we examine whether each piece is acidic or basic or neutral. And only the non-neutral conjugates will contribute to pH. Does that make sense? Because the neutral ones are just, they're nothing. So here's how we do this. Imagine you have NaCl, regular salt, NaCl. To figure out, so NaCl first of all is Na plus and Cl minus. These are the conjugates that it's made of, Na plus and Cl minus. To figure out if Na plus is acidic, basic, or neutral, I need to track down what it must have come from. And here's how you backtrack the acid or base that it must have come from. It's a positive ion, right? You have two options here. You can either tack on an H plus, or you can tack on an OH minus. If your conjugate is negative, then you would combine it with H plus, right? If your conjugate is positive, then you will tack it on with OH minus, because acids and bases are neutral. So if you have a conjugate, tack it on with the oppositely charged H plus or OH minus to get the acid or base of origin. So Na is positive. So what acid or base it must have come from?
OH minus.
So yeah, it's positive, so I'm tacking on an OH. Great. I have done my reverse detective work. It's NaOH. What about Cl minus? What acid or base must it have come from? Say that again?
HCl.
HCl. Great. Is NaOH a strong acid or a strong base?
Strong base.
Strong base. So what is the nature of Na plus? Acidic, basic, or neutral? Neutral. Good. So this part of the salt, this conjugate, is neutral. HCl, strong acid or strong base? Strong acid. Good. So the conjugate is neutral. Both conjugates are neutral here. So what must be the pH of NaCl solution? 7. It's neutral. This is called a neutral salt because it's made of neutral conjugates. Okay. So it's very important that you memorize the table with, or a short list of strong acids and strong bases, because you'll need to do this analysis. All right, let's work with another one. Yes. CH3, COO, and A. What two ions, what two conjugates is this made of?
CH3COO minus.
CH3COO minus, good. And?
Na plus.
Good. And so this must have come from? It's negative, so you tack on the positive thing, H. Yeah? It's positive, so you tack on the OH minus. This must have come from NaOH. NaOH, like we saw last time, is a strong base, so this part is neutral. What about this? Louder. It's acidic, strong or weak?
Weak.
Weak acid, good. This is vinegar. Acetic acid, so this must be basic, good. So the broken piece must be basic. Good. So we can't exactly figure out what the pH of the solution is without doing a calculation, but qualitatively, would the solution be acidic, basic, or neutral? Basic, right? You have a basic part, a neutral part, so effectively it becomes basic. So that is a basic salt. You might expect questions like that on the exam. Here's a salt. Figure out if it's acidic, basic, or neutral. Break it down into its pieces, reverse engineer the acid or the base that it came from, and then answer the question.
So for the previous one, would you call it a neutral salt?
Neutral salt. Yeah. That's why salt water doesn't burn. Yeah. When you dip your hands in the ocean, it doesn't burn because it's neutral. Salt is neutral. However, if the ocean had a lot of, this is sodium acetate, very cool salt. If it would have tons of sodium acetate in it, then it would burn because the ocean would be highly basic. Right? Magnesium salt. I think Epsom salt. Have you guys used Epsom salt for baths? Epsom salt might be not neutral. It might be slightly acidic or basic. We'll figure it out. Okay, anyway, so you get this analysis, right? Any questions? Do you want me to go over another example? Yes.
Some of the questions, they also had like, instead of coefficient of 1, they had like associated to 2, like BaOH.
Yeah.
I was confused on those ones.
Where you have coefficient?
Like, so the formula is like, it's in the solution of barium hydroxide, so it's BaOH2, and then it's dissociated to 2 OH, and then plus 1 Ba, and then that one, how we calculate the pH, because there's 2 hydroxide now.
Your ice table will just have the,
2x squared?
yeah, it will have the 2's carrying on from, yeah, nothing special,
It's just
just that, yeah. So the question is, what do you do when you have acids or bases, strong acids or strong bases, where you get 2 OH minuses? So for example, barium hydroxide, which is I think a strong base, that dissociates into this and 2 hydroxides. Oh, nothing changes. Blah, blah, blah. This is going to be minus x plus x. The only change here is this is going to be plus 2x because of the coefficient. Yeah? So the only changes that happen if you have multiple hydroxides or multiple H pluses popping up on the other side is the usual changes that you make in the ice table. Nothing else. So you do this whole analysis. Oh, and one more thing. So suppose this was 0.5, 0, and 0. So this will be 0.5 minus x, x, and 2x. When you set this up, x, 2x squared, 0.5 minus x equals, I don't know, some kb. Was that for strong acids or strong bases? Or was it for strong stuff or weak stuff?
I don't remember.
Okay. I don't think it's, oh, never mind. It's not ice table, I'm sorry. If it's an ice table question, you'll always dissociate only once. Exactly once. So for example, what's a diprotic weak acid? I think phosphoric acid is not that strong. H3PO4. It may be a strong acid, but for a second, think of it as a weak acid. It is capable of giving up 3 H pluses. Okay? But for ICE table questions, which is exactly what you will be tested on, you only want to dissociate this once. So take out only one H plus. So what's left? Two H's are left, and a PO4 is left. This is your equation. You're not going to dissociate this into three H pluses, just one H plus at a time. Okay? Yes?
Sorry, I remember doing a problem similar to this on Alex, but it seemed like it was a titration.
Yeah, that's coming up.
Okay.
Titration is a separate story.
Okay.
If you're doing pure weak species questions, not mixtures, just calculate the pH of H3PO4 in solution and you're given a Ka value, you only break it up once, H plus. Because the reason is, this reaction has a Ka value, right? Call that Ka1. When you break it up a second time, this thing, the Ka value is going to be different. It's called Ka2. Break it up a third time, Ka3. So this is the first Ka. This thing is it's possible for you to break it up again. It loses an H plus to become HPO4 2 minus. That has a separate Ka value, Ka2. And then lastly, this thing can break up again. And that has a third value, Ka3. But you're not going to deal with this. I'm just saying this is how it goes. You're only going to deal with this first part. That's all. Okay? Generally, it becomes harder and harder as you go down. For an acid that's multiprotic, that is capable of giving up more hydrogens than one, the first hydrogen is easily given out. So this is going to be a big value. This is going to be a smaller value. This is going to be a very small value. Right? So, okay. However, in the case of strong species, coefficients, you want to break it up completely. Barium hydroxide. I think, yeah, barium hydroxide is pretty strong. So here's the question. Calculate the molarity of 0.5 molar barium hydroxide. Jesus, it is burning in this room. So what's the pH of this thing? This is strong. Strong stuff dissociates completely. That's the hallmark of a strong species. So this is going to break up into Ba2 plus and 2 hydroxides, 2 OH minuses. So all of it's going to get consumed to produce 0.5 and what's the number here? If 0.5 molars of barium hydroxide dissociate, it dissociates into 0.5 molar Ba2 plus and how many molars of OH minus? Careful, so every BaOH2 molecule breaks up into 2 OH minuses.
So 1 molar?
Yeah, it doubles, right? If I have 2 molecules of BaOH2, they will break up into 4 OH minuses. Because each BaOH2 breaks up into 2. Does that make sense? No?
Like, where does that extra?
Oh, this extra came from the chemical formula of barium hydroxide, which had a 2 there.
No, like, where does this, like, this extra amount of OH come from?
No extras. Suppose you have a goodie bag that has 1 bottle of water and 2 candies. If I give you 1 goodie bag, how many candies do you have? 2. If I give you 5 goodie bags, how many candies do you have?
10.
Same thing here.
Oh, okay. Okay.
So, because of the coefficient, this is going to be 1.5 times 2. So what can I calculate here? pH or POH? POH. is going to be the negative log of 1, which if you calculate it becomes 0, and so pH is, yes, 14.
So we don't have to do an ice table for this one, we can just calculate it because it's.
Yeah, you never do ice tables for the strong stuff. Because you know what it breaks up into. You know exactly what the molarity is going to be when it breaks up. Because it dissociates fully. Okay? Key takeaway. For strong stuff, pH calculation, strong acids, strong bases, no ice table. Ice table only for weak stuff. We'll see in titration. We'll get there. Okay. Getting too ahead of us. All right. Moving along. So we have discussed pH of salt qualitatively, right? We can say whether the pH is going to be 7, i.e. neutral, more than 7, i.e. basic, or less than 7, i.e. acidic. Now let's do a quantitative calculation. So figure out exactly what the pH is going to be. Here's a question. Calculate the pH of a 0.5 molar CH3COONA solution. Given that Ka is 10 to the negative, I'm just going to make it up, 10 to the negative 8. Okay, this is a salt. It's made of 2 conjugates. I'm going to break it up into its pieces. I don't know why, but okay. We have some time. This is the active part, this is the non-neutral part.
So you said that if the conjugates are neutral, they're weak?
If the conjugates are neutral, then they're neutral. If the conjugates are acidic or basic, then they're weakly acidic or weakly basic. Yeah, conjugates, yeah. The acidity and basicity that they have is weak. Okay, so this is what do we figure out? This came from CH3COOH, which was a weak acid, so this is basic. Okay. Bases react with water and they accept an H+, so this becomes CH3COOH. And what's left of the water? OH minus. Good. Ka or Kb? OH minus. So I need the Kb value here. What do I have? Ka. So what's, if that's 10 to the negative 8, what's Kb? 10 to the negative 6, right? 10 to the negative 14 divided by 10 to the negative 8, which is 10 to the negative 6. Great. And then business as usual. 0.5. Don't care, it's water. Nothing. Minus x plus x plus x. 0.5 minus x, x, and x. You have products up top, reactants at the bottom. 10 to the negative 6, small x approximation. Once you do this, what do you get? pH or pOH? Right. And then minus, and you have the answer. So, once again, with salts, what do? Break it up into its pieces, and then you can have a lot of possibilities. You can have both of them, both of the conjugates be neutral, in which case the solution is entirely neutral. pH is 7. Okay. You can have the case where one of the conjugates is neutral and the other one isn't. In that case, you ignore the neutral one, and then you write down the acid or base reaction by reacting it with water for the acidic or basic conjugate. You will never be given a case where one conjugate is acidic and the other conjugate is basic, because that's complicated. Because now both of them affect the pH and they're competing with each other. We're not going to touch that. We're only going to go as far as 2 neutral conjugates or 1 neutral and 1 non-neutral. Got it? Okay. Let me do another question in this topic and then move on to the next one. Actually, let me move on to the next topic. We have too many things to cover. Okay. Now let's mix up weak stuff and its conjugate. So from here on, we'll only be talking about mixtures, various different kinds of mixtures. Here comes the first one. This is the first mixture that we'll be talking about, weak and its broken piece. And the second mixture, the last topic of the chapter, will be a mixture of a strong species and a weak species. And then we're done. This combination is called a buffer. And this is very easy. Provided that you memorize these 2 equations. These are called Henderson-Hasselbalch equations. First one, so there's one for acid plus its conjugate. And then there's one for base and its conjugate. This one is pH equals pKa plus log. I like to remember it like this. Concentration of the conjugate divided by concentration of the acid. You might see in Alex or in your textbook, this is written in a weird way, where it's A minus over HA. I don't like that. Conjugate over acid. Base, so take this whole equation and make it basic. pH becomes POH, pKa becomes pKb. Conjugate is still there, but now instead of acid I have base. Again, here's a question. Calculate the pH of a solution that is 0.5 molars in CH3COOH and 0.3 molars in BaCH3COO minus. Whew. Tell me if it dies again. Okay, so this topic is easy because it's plug-in chart. It died? Oh, okay. So what do we have here? Here's my acid. This is the weak acid. And here's my salt. The salt is consisting of two things, Ba, 2 plus. Okay. Let me take this equation, the Henderson-Hasselbalch thing, pH equals pKa. Have I given you Ka? No. So let's say Ka 10 to the negative 8. What's pKa? Given the Ka value? 8. Negative log of that, 8. Plus logarithm of concentration of the acid, 0.5. Concentration of the conjugate. What do you think it is? Say that again? No, you're right. What did you say? Oh, well, 0.5 is down here. It's already there, yeah. 0.3, 0.6, because, look, it's 2 copies. Right? Salts break down completely because they're salts. Unlike acids and bases, break down into Ba, 2 plus, and 2CH3CO minus. So you gotta watch out for this. This is 0.3, 0.3. This is 0.6. Gotta be careful. All right, so that's 0.6. And that's it. Put that in a calculator and you're done. Because this section is easy, they will try and throw you off with things like these. And they have these respective volumes, V1 and V2. When I mix them up, I get a total solution. It's a mixture of the two. Both of those molarities are going to change. Does that make sense? Not because the number of moles have changed of each substance, but because the total volume has changed. Okay? So the new molarity here is going to be, M1 is going to change, let's call that M1 prime. M2 is going to change, let's call that M2 prime. And what's going to be the new volume? V1 plus V2, right? Two different things. The volumes are just going to add up. That doesn't happen with molarities, otherwise life would be easy. Would be easy. So that's just V1 plus V2. So how do we calculate these new molarities of solutions 1 and 2 in the combined solution?
Initial and added, on the base or the acid.
Yeah, dilution formula. M1V1 equals M2V2. So for the first one, M1V1 equals, in the final thing, it becomes M1 prime. And what's the final volume of the solution? V1 plus V2. So if you solve for the new molarity M1 prime, it is M1V1 plus divided by V1 plus V2. And similarly, for the second one, M2V2 is M2 in the combined solution with a total volume of V1 plus V2. And so M2 prime is M2 V2 divided by the total thing. These are molarities in combined solution. Molarities in combined solution, which are different from the starting solutions. This is how you calculate it. You don't need to memorize these formulas. Just know the process. Okay. So anytime there's mixing of solutions, this is what you do. This is going to be very important in titrations, but not important in Henderson-Hasselbalch. And let me give you an example of that real quick. You know what? I will do titrations next time, so I can have the camera cool that. Or you know, I'll record a separate lesson of titration and then just tack it on to the recording and make that a whole thing. And when's your homework, Alex homework due for acids and bases?
He extended it.
Huh?
He extended it.
To Monday. I'll try and record a session before Monday and send it to you. Okay, so the last thing that I want to discuss today is this molarity versus moles business. Is it still recording? I guess. Just don't die on me. Calculate the pH when 300 milliliters of Yes, 300 milliliters of 0.5 molar CH3COOH is combined with 200 milliliters of 0.3 molar BA CH3COO twice. Same combination as the last question. So contrast this question with the last one. In the last one, notice how I worded it. A solution that's 0.5 molars, I'm talking about the last question. 0.5 molars in acetic acid and 0.3 molars in barium acetate. What I mean by that is those are the molarities in the combined solution. Okay? So I've already given you don't have to work it out. I've already given it to you. Here, I haven't given you the combined molarities. Here I've given you the starting molarities before mixing. That's the big difference. The molarities, if you input molarities into Henderson-Hasselbalch, they have to be the combined molarities, not the initial molarities, which I had given you in the last question. Here, I've given you separate molarities, so here you're going to go the other route, which is input moles or millimoles, as opposed to molarities of the combined solution. Because oftentimes doing this is going to be far easier than figuring out the combined molarities. Still recording. Okay. So in this question, pH is going to be pKa, Ka same as last time, 10 to the negative 8, 8 plus log. Instead of molarities, we're going to plug in moles. How do you calculate moles if you have volume and molarity? Huh? Multiply, exactly. If you multiply them, you get moles. But notice here, this is in milliliters, right? And so you're not gonna get moles. If you multiply milliliters and molars, you're gonna get millimoles. No problem. You don't even need to convert this into liters. Just multiply these two, you get 150 millimoles. Just multiply these two, what do you get, 60? 200 times 0.3? 60. 60 millimoles. But just be careful because this is acetate, 2 copies, so it's going to be twice the number of millimoles.